Hi everyone, I'm Prof.K and welcome back to my channel. If you've seen my other videos on voltage drop calculations, you already know how important this topic is for both the Canadian Electrical Code and the National Electrical Code. In this short lesson, I'm going to derive the voltage drop length formula directly from Ohm's Law, step by step, so you can understand where it really comes from, not just memorizing it. Let's get started. Is in National Electrical Code, Chapter 9, Table 8, and the Canadian Electrical Code, Section 8, Table D3. I'll show you where it is. Here's the National Electrical Code, Section 9, Table 8. The Canadian Electrical Code, it looks like this. This is Table D3, and these are K factors that sit in this table as well. And they're called K values, but they're sort of like a resistance, but they take into account the some thermal conductivity changes, so they're a little bit on the conservative side. They're a little bit higher than resistance, and this voltage drop depends on the power factor, and it depends on how it's installed, because the heat dissipation is going to be different for how it's installed. And the formula is sitting right down here, and if we look at the next page, the formula is written in terms of K, and it's written in terms of L as well. So that is the same formula, and it's just rearranged. It has a value here, which is a voltage drop factor. It's going to be for the factor F. But anyway, let's look at this formula and see where it actually comes from in physics, because I can explain that to you. In the code book, there are not any units explained, and it's really important to look at these units, because you notice both in the Canadian Electrical Code and in the National Electrical Code, you have this factor of 1,000. That's because this K value in the Canadian Electrical Code and in the National Electrical Code is expressed in units in that table. If you look closely, it's in units per kilometer in the Canadian Electrical Code, and it's in actually ohms per kilometer, and ohms, which is our resistance value, it's ohms per 1,000 feet in the National Electrical Code. So whether you're in metric or imperial units, you're still converting by 1,000 to get rid of this kilometer or 1,000 feet, because you want this one expressed in feet and you want this one expressed in meters, not kilometers. So conveniently, no matter where we are using this same formula. I'm showing here in metric, so I have meters per 100 kilometers, but that 1,000 feet in 1 foot is what the National Electrical Code would have that 1,000 there for. So the length is in meters, and of course we need to install less than or equal to this, which is our voltage drop times that 1,000 conversion factor times the current, the load current. The load current in amps, and this K value, again, ohms per meter, or ohms per ohms per kilometer, or ohms per 1,000 feet. F is a factor, and it is how many runs. It could be outgoing and return, then F would equal 2, and it's often equal to 2, and it's unitless, and voltage drop is expressed in volts. So you have to sort of do your voltage drop formula for that, which is a ratio that is in percent. You know, apply your voltage drop formula to the voltage of the problem or of the installation. Okay, so where does this formula come from? It comes from Ohm's Law. So let's take a look at Ohm's Law. Ohm's Law is V equals IR. This is Ohm's Law, where the resistance is the total resistance, and of course that would be the resistance per length times the unit length, right? Times the length. That's what would give you resistance. So we would want resistance per unit length. That's called linear resistance. And forgive me, I'm going to do this in metric, but you can comment below and have an argument about imperial versus metric, but I'm going to do this in metric. That's in ohms per kilometer on the chart, right? And Length, I can just call L in meters, because we like expressing length in meters, and I know that this formula has length in meters, so that's why I'm expressing it in meters there. And because of expressing it in meters there, if I want this total resistance R in ohms for Ohm's law, in ohms for V equals IR, because I want to sub this into V equals IR, which is equation 1, then it has to be in ohms. So I'm going to have to convert then kilometers into meters. So I'm going to have 1 over 1,000 here, because kilometers in the denominator, there it is. I have to put this in the numerator. So now I have resistance in ohms is equal to this linear resistance, which is K, in ohms per meter now, times length in meter. Okay, so now I'm going to substitute that. I'll call that equation 2. I'm going to sub that back into Ohm's law. So now I sub 2 into 1, and I'm going to see if I get this formula up here that I'm trying to not prove but illustrate. So I'm going to sub 2 into 1. 1 is V equals IR, and that's I in amps. I want V in volts, right? I in amps, and R is now all of this. Now R is all of this. It's going to be K in ohms per meter. It's going to be L in meters. Yes. And what if I rearrange for L? Then, because this is in terms of L, so I'm going to do L in meters is going to be V in volts. And if you don't remember how to rearrange equations, you can put a comment below, because some people are out of school for a long time. But I'm simply rearranging this equation to isolate L, because it's isolated up here. So I'm seeing voltage drop. Yes, I've got this voltage drop. I've got current in the denominator like I wanted to. I've got K in the denominator here. I don't have this factor of 2. That's because I actually, that factor of F. This is going to be for a length L in meters. We want there and back, it's 2L. So let total length be F times L. So really, I should have had F times L here. I'm going to multiply that by factor F. Now, factor F is over here, but I want to isolate L, so factor F has to go in the denominator over here. So now I have I, K, and F. I don't have the 1,000 because, silly me, I converted over to meters here because I knew I wanted to be in meters, and I wanted to have the resistance as a resistance. So now, yes, of course, I wanted to do that. However, the silly thing is that K is actually not expressed in ohms per meter, even though I wanted my resistance in ohms to show you that it plugs directly into Ohm's law. So I'm going to say, but the code books, they don't give us K in ohms per meter. They give us K in ohms per kilometer, 1,000 meters. And they don't give us K in the National Electrical Code in ohms per foot. They give it in ohms per 1,000 foot. So therefore, I need to express this in ohms per kilometer or ohms per 1,000 feet, because I'm trying to match this formula up here. So I'm going to have my voltage in volts times my current in amps times my K in ohms per kilometer or ohms per 1,000 feet times F. And since I did that, now I've messed up Ohm's law. I have now length is no longer in meters, and this is a false statement I'm circling here, But in order to make it a true statement, I'm going to multiply the numerator by 1,000 meters per kilometer. That'll get rid of the kilometer in the denominator, and the denominator I'm left with volts times meters over amps times ohms. And if we remember our units, you're going to ask me, is that true that we should have a volt time? How does a volt times, here, I'll do the whole thing, meters per kilometer over amps times ohms per kilometer, and of course F is unitless, so the kilometers cross out, and that equals volts times meters over amps times ohms. And then I want you to remember V equals IR, so let's look at the units. It's volts equals amps times resistance, right? And so if I then sub in amps times resistance for voltage here, I get amps times resistance. Oops, that was a strange way to express that. Amps times resistance times meters over amps times resistance. Amps and resistance cross out. I am left with meters. I am left with meters. So, and that was for length. Length equals all of this. Kilometers cross out, and our ohms, volts, and amps cross out because of Ohm's law that I just showed you here. And all of this ends up being in meters. Length on this side in meters. V, 1,000, I, K, F, all in meters down here. We have, let's double check. We have length in meters up here. We have V, 1,000, I, K, F here. This equals this. And we have illustrated that the formula in the National Electrical Code, Chapter 9, Table 8, and the Canadian Electrical Code, Section 8, Table D3, is indeed directly from Ohm's Law. Thanks for watching. I hope this helped you see how the voltage drop formula relates to the regular Ohm's Law formula. It's pretty simple, right? If you found this useful, please like, subscribe, send me some comments. I always enjoy your thoughts and comments, and we can have a discussion. And thanks, I'm Prof.K, and I'll see you in the next class.